Now we're going to talk about the conformations of butane. There's going to be four important conformations to know for butane itself. So first, we're going to take a look at what the molecule looks like when we're just looking at it on its side. So butane has the four carbons, and if we want to transfer the carbon numbers to our model kit, we're going to have a carbon 1 being represented by that green ball. That's going to be a CH3 group in our representation. Carbon 2 is going to be the one beside that. Carbon 3 is going to be the one beside that. And then carbon 4 is going to be the other green ball in our representation. And so what we're seeing with this one, the way that we're looking at it, we do have H's, one going out of the page. So that's this wedge H right here. Then we have one going back into the page, which is this hash H right here. And then on carbon 2, we have the hash H going back into the page, which is seen right here. And then the one that's coming out towards us here is that wedge one right here. The 1,2 bond is this bond. The 2,3 bond we're looking down and are therefore not going to see in any of the other pictures is going to be this bond right here, because we're going to be looking directly down it with carbon 2 in the front. And then the 3,4 bond is represented by this line here. And so we're going to take a look at our first conformation by just rotating this and looking down the 2,3 bond. So we're going to look from this angle directly down here. What we would expect to see is we'd expect to see this CH3 at the very top of the front atom. We expect to see this H on the left, this H on the right, because we're looking from this direction, and then this H on the left, this one on the right, and then this one straight down when we're looking from that direction. So let's see. This is the picture of looking directly down that bond, so that representation we were just talking about. Now this is carbon 2 in the front. If we want to number them all, carbon 1 corresponds to that green ball at the very top. Carbon 2 we can see at the front there. Carbon 3 is back behind there, so I'm just going to put a little arrow because we can't actually see it in this diagram, so we're looking directly down that bond. And then carbon 4 is that green ball that's representing that CH3 group. So we see in this representation from just turning that molecule in that zigzag structure that we do have this the two CH3s as far apart as possible. All of the atoms are staggered from one another. And so our upside down Y is at the front here. That's this. And then our back atom we can't actually see, so we're doing a circle. And then this H is this H, this H is this one, and the CH3 is down here. This conformation is called the anti-staggered conformation because the two largest groups are exactly opposite to one another. So they're 180 degrees apart. We have that maximum separation. It's actually the most stable of the conformations of butane because those two large groups are as far apart as possible. And that means so more stable translates to lower in energy. And so this is the lowest in energy conformation. And that's why we typically draw the carbons backbones as a zigzag because that is the staggered conformation for that molecule. For any kind of carbon chain, it's staggered when we draw it in the zigzag, and that's why we always draw it like that, because we just draw the most stable conformation. So this is the anti-staggered conformation. When we rotate it 60 degrees, we had brought the CH3 that was on the top, we just brought it over 60 degrees. And so we're going to have now that CH3 to the right. So that corresponds to that same green ball. Then we have carbon 2 in the front. We see carbon 3, we see just a tiny bit of it because we took this on an angle just so that we could see the different carbons and the different bonds. And then 4 is the green ball back there. And so we have this is the CH eclipsed conformation because we see that the bonds are actually going right on top of each other, and our CH3 carbon 1, that CH3 is overlapping with one of the H's, and then carbon 4 CH3 is also overlapping with one of the H's. We draw those lines slightly off just so that we can see that they're there, just like this picture was kind of taken slightly off so that we could see that everything was there. So this H would correspond to the same one, so we actually left the back the same. and then this H is this one over here. And then the front atom makes kind of still a little bit of a Y like that. So this one, because the big groups are overlapping another atom, it's going to be higher in energy than the anti-staggered, but we're going to see it's not going to be actually the worst conformation that is possible. Another 60-degree rotation. So we took that front atoms. Notice we're keeping that back atom exactly the same. We're just rotating the front one. Doesn't matter which one you rotate, as long as you pick only one and you're rotating it around. And so this time now we brought, from our previous one, our CH3 was up here. We just brought it down another 60 degrees, and same with on this. So if we want to transfer our numbering to here, our CH3, number 1 is there. Number 2 is in that front there. Carbon 3, we'll put another arrow to it because it's directly behind, so we can't see it. And then carbon 4 is that CH3, that green ball. So this conformation, it is staggered. We can see that from our Newman projection. We can see that from our model that all of these bonds are actually staggered from one another. However, the two groups now, the two CH3 groups, are actually closer together than they were in our original conformation, and that's seen here as well. This is called the gauche staggered conformation because we have these two groups, these two large groups in this gauche conformation. So they're go gauche to one another or close to one another, but not right on top of each other, not across the ring from each other. They're pretty close though, and so we don't have the maximum separation of these big groups. And so although it's pretty low energy and stable because it is a staggered conformation, it's not the most stable because it's not anti-staggered. Those groups are closer together than what they were in that anti-staggered conformation. So for this last conformation, we're going to take this CH3 group and this front atom and rotate it 60 degrees back down to make the worst conformation. That is the eclipse, the CC eclipse, because both of these carbons are going to be eclipsing one another. If we wanted to put our numbering onto this model kit, we have carbon 1 there, 2 in the front there, 3 we can barely see at the back, and then 4 is that green ball there. So we do see that they're overlapping completely right here. Remember that these are not just little balls, they are actually a carbon atom that has other bonds to H's. And so they're starting to get in the way because each of these has their own bonds to H's. And then this also has its own bonds to H's. And so the H's and those electrons in those bonds are starting to interact. And that's what we call a steric interaction. So we have a pretty bad steric interaction here. We can represent it with these kind of two half brackets or half moons, and we can say steric interaction. That is what we call the interaction between the two groups that are kind of too close to one another in a molecule. It's a high energy situation because both these groups have electrons in their bonds, and those electrons are getting close to one another as the groups get close to one another. So that's kind of why groups on a molecule don't really like to be close together. They kind of like their own space so that their electrons can have their own space and not have that electron repulsion. And so this is a pretty bad steric interaction. We had it as well with the CH eclipse, but the steric interaction was between a carbon and a hydrogen, not as bad. These two, those hydrogens are shooting out in all the directions, and so they're going to actually end up interacting pretty badly here. So our large groups are eclipsed. It's the highest energy and the least stable conformation. So the CC eclipse, where these two groups are right on top of each other, worst conformation. Second worst would be the other eclipse conformation where the CH3 was on top of the H, so the CH eclipse. That's the second worst, or the second least stable conformation. The second most stable conformation is the gauche staggered one that we saw right before this one. And then the most stable is the anti-staggered. And so that's kind of how those conformations go. As we rotate, as we keep going, if we rotate again, we're just going to get another gauche conformation and then another CH eclipsed and then back to the anti-staggered. So we do these rotations in real time in the video that's posted after this. We'll see it for ethane and for butane so that you'll get an idea of what does that look like a little bit more in 3 dimensions and in real time doing that rotation, so you can maybe do it yourself with your model kits as well.